Indeed, for the invitation to present again at this instructional course for Aman and Johnny, and for Uretna for inviting me. It's a pleasure to be here. This is very much a prelude to the subsequent talks that are going to come later on in the session, and it's deliberately pitched at a clinician's level for ease of accessibility. These are my disclosures. So I'm just going to overview what I'm going to talk about. I'm going to initially outline tamponades at a basic level, then move on to some commonly used definitions and hopefully clarify some potential confusion that may exist. Then I'll talk very briefly, again at a clinician's level, about the chemistry of silicone oils and PFCLs before summarising and closing. We are all aware that a tamponade agent provides surface tension across a retinal break, thereby preventing further flow into the subretinal space until our retinopexy provides a permanent seal. That's what helps to make our retinal detachment operation work. And we may or may not know that tamponade agents have evolved quite significantly over the last 100 or so years. And now, as vitreoretinal surgeons, we have a wide variety of tamponade agents available to us in the form of gas, oils, perfluorocarbon liquids, and heavy oils. And they sometimes come with mystical numbers on their packaging, mystical numbers in their product specification, and I hope to demystify that a little bit today, if possible. So moving on to the definitions, I'm going to talk a bit about density and specific gravity, then viscosity, surface tension, miscibility, and I'm going to touch on emulsification. So density, well, in some contexts it might be considered depicted in any of these three images, but of course we know that density is a product or a function of a substance's mass divided by its volume. And we all know that the denser the substance, the relative densities determine the position of two substances. We may be presented with a number or a figure for specific gravity. That can sometimes come in the product information leaflet of our tamponade agents. But since specific gravity is a function of the density of water, and for all intents and purposes the density of water is 1, we as clinicians can use those two words interchangeably. So specific gravity and density are essentially the same thing. So armed with this knowledge and knowing the relative densities of two liquids or agents or substances, we know that a gas bubble will both float in a bubble of silicone oil and in PFCL because it's less dense. And a water bubble will sink in silicone oil because it's more dense and will float in PFCL because it's less dense. Viscosity. Viscosity is defined as the property of a fluid to resist the force tending to cause fluid to flow. That's all very well. What does that mean? It's expressed in chemistry-wise in terms of millipascals, but as clinicians we're more used to using or being presented with center-stoke or center-poise, all of which can be used synonymously with each other. I think we use center-stoke in the UK. Center-poise is more used on the continent. But what does that mean for us? Well, really what it means is, depending on the viscosity, it determines that an agent will require a different injection force and therefore different tools or machines to get the agent in or take it out of the eye, depending on its relative viscosity. A question that we are sometimes presented with is there any relationship between viscosity and density? I don't care how good you are at maths. But you shouldn't be able to find a formula that relates these two things. So no, viscosity and density have no relationship to each other. Emulsification, that is the dispersion of one liquid in a second immiscible liquid, but really in practical terms we know it as the formation of smaller droplets due to the breakdown of the original bubble. Why do we care about that? Well, we want to avoid, if where possible, the conditions or the clinical presentations of what we have in the pictures at the bottom of the screen. What is it that affects emulsification rates? And perhaps more relevant and topics of discussion is viscosity and emulsification related, because we are led to believe as clinicians that if we use an oil or an agent that is a greater viscosity, that would be the preferred agent for a long-term endotamponade. So in part, yes, that's true, but we mustn't forget that there are other factors that may affect viscosity, namely the shear stress on the bubble, the presence of surfactants, and the presence of oil impurities that may actually act as surfactants, which can reduce the surface tension of the oil bubble. And we all know that surface tension is what encourages a bubble to stay as a single bubble. Briefly, silicone oil chemistry, very briefly, because I think most of us are clinicians here. Silicone oil is a polymer, a linear polymer, so a long chain of silicon and oxygen. It consists of this repeating unit of polydimethyl siloxane, and its properties are dependent basically on two things. So the length of the chain, the number of repeating polydimethyl siloxane units determines the length of the chain, and therefore the longer the chain, the greater the viscosity. So 5,000 center-stoke or center-poise oil has a longer chain, about 700 repeating units of the polydimethyl siloxane, and 1,000 has about 380 repeating units. So properties, first of chain length is related to viscosity, and also the greater the proportion of a particular chain length determines the homogeneity of the oil. So the narrower the distribution, the more defined the oil property. So the more of a particular chain length you have, the more predictable the substance will be able to behave. Very briefly, I've included this slide, but Johnny Smith's going to elaborate a bit further on oil impurities, but they're relevant to this talk. Oligosiloxanes are production-related compounds of low viscosity, and aside from, there's a list of them there, don't expect you to read them because they're unpronounceable. But oligosiloxanes and silanols are impurities that may occur during the manufacture processing, and aside from their direct or indirect toxic effects on the retina, they may affect the physical properties of our oil bubbles through their reduction on surface tension, because they, as I've referred to earlier, they may act as surfactants and reduce the surface tension and perhaps increase emulsification rates. One slide on PFCl chemistry. So perfluorocarbon liquids are fully fluorinated carbon liquids. We tend to use two commonly, or we're aware of two commonly, PFO and PFD, perfluorooctane and perfluorodecalin, but don't forget C2F6 and C3F8 are also perfluorocarbons, but they're gas. We use them because of their properties. They're optically clear, they're highly dense, and they have low viscosity, so we can inject them through a syringe. We don't need any special tools to get them in to the eye. They are highly hydrophobic, and they should be chemically and biologically inert by definition, and they should be non-toxic in their purest form. This final slide summarizes the characteristics, the physical and chemical characteristics of silicone oil and PFCl that I've referred to in the talk. So to summarize, the density or specific gravity of an agent, of two immiscible agents, determines its relative position. Viscosity of oil is dependent on the length of the polymer chain and may in part, but not wholly, be related to emulsification rates, because there are impurities that can be related to the production process that may affect the chemical and physical properties of silicone oil and PFCl. Thanks very much indeed.
Thanks very much, Phil. For the sake of time and progress through the presentation,